Okay guys, today we're going to continue with section 10.2. This was our section again on arcs and chords. Today we've got 4 theorems that we're going to be focusing on. So I just want to make sure that you guys are comfortable with these 4 theorems. The first one says that in the same circle, or in 2 congruent circles that we know would be congruent because they're marked with their radius being exactly the same measure, 2 minor arcs are going to be congruent if and only if we have a biconditional statement, their corresponding chords are congruent. So let's take a look and see what this means, what this is going to look like. First of all, in an example where we've got 2 chords in the same circle, if we know that these chords are congruent, that would also mean that the arcs were congruent. Also, if we knew that the arcs were congruent, that would mean that the chords would be congruent. Because it's biconditional, it works both ways. So let's go ahead and start off with, if we know that arc AB is congruent to arc CE, then we know that segment AB is congruent to segment CE. Again, because it's biconditional, it works the other way too. So instead of saying, if we know this, then we know this, if the arcs were congruent, then the segments would be congruent, we could also say the arcs are congruent if and only if the segments are congruent. Because I could also write this backwards and say, if I knew that AB was congruent to CE, then I also know that arc AB is congruent to arc CE. Now, if we have 2 circles that are congruent, then again, we know that because these circles are congruent, then we can still compare those arc measures, or arc lengths. So I can say that, again, arc JK is congruent to arc LP if and only if segment JK is congruent to segment LP. So we have 2 biconditional statements. If the arcs are congruent, then the chords are congruent. If the chords are congruent, then the arcs are congruent. It goes both ways. All right, now, next one. It says, if a diameter of a circle, so I've got a diameter, EG is the diameter right here. It goes through the center. Its endpoints are on the circle. If we have a diameter of a circle that is perpendicular to a chord, so again, I've got a chord marked here. Chord has 2 endpoints that are on the circle. If a diameter is perpendicular to a chord, then it will also bisect that chord. So looking at this, I've got a perpendicular bisector. Now, knowing that, we could talk about the perpendicular bisector theorem to say that, again, this chord ED would be exactly the same measure as the chord EF. So we could talk about some other things here that are going to also be congruent. But if we know that EG was perpendicular to DF, then we know that it bisects. So I could say that DH would also be then congruent to HF. All right, the next one says that if one chord is a perpendicular bisector of another chord. So I have 2 chords here, and if I tell you that I know that one is a perpendicular bisector, so JK is a perpendicular bisector of the other chord, then the first chord has to be the diameter. There's just no other way about it. It has to be the diameter. The last theorem that we're going to be taking a look at, it says in the same circle or in congruent circles, if 2 chords are going to be congruent, if and only if we've got a biconditional. So when 2 chords are congruent, then they're going to be equidistant to the center. So if the chords are going to be the same length, then they're both the exact same distance to the center of the circle. So if I know that If I know that CD is congruent to AB, then I know that the measures to the center, so I could say that FE is equal distance to GE. Same thing would be true if I wanted to talk about congruent circles. That again, if these chords are congruent, then the distance to the center will